GitHub powers millions of developers every day, and when it went down, Twitter immediately had a theory. Too many people vibe coding, AI finally broke GitHub. Sounds convincing, except that's not what actually happened. It was not a massive bug or a data center failure. It started with one small component that almost nobody thinks about. And that's where our story begins. Before we understand why GitHub went down, we need to meet our main character of the story, the sidecar. Think of it as a bouncer standing in front of your application. So every request coming in or going out has to pass through this bouncer first. And that's genuinely a brilliant idea because this bouncer can handle things like encryption, automatic retries, timeouts, and traffic metrics without your application having to implement any of it. So in Kubernetes world, this is commonly done through using a service mesh like Istio. Istio manages how services communicate with each other, while Envoy is the proxy that actually sits beside each application and handles the traffic. So think of Istio as a traffic manager and Envoy as a bouncer standing beside your application. But like every other engineering decision, it comes with a trade-off. And that's exactly where GitHub story takes a turn. Because now, every request has to pass through two components, your app and the sidecar. And that means the sidecar can become the limit of your application. So for example, your application might be able to handle 10,000 requests a second. But if the sidecar can only handle 1,000 requests at a time, those extra requests have nowhere to go. So even though your application has plenty of capacity, your system can only handle what the sidecar allows. And here's the fun part. Those proxy limits are often set when the cluster is created and then they are quietly forgotten. So as a developer, we usually do this kind of mistakes, right? So since I'm a developer, I'm going to ignore this. So which is exactly where things started going wrong for GitHub. The sidecar hit its concurrency limit. And just to make things clear, concurrency simply means how many requests the proxy can handle at a time. So once it hit that limit, requests started getting rejected. Normally, this is exactly the kind of problem Kubernetes is designed to handle. It can automatically create more copies of your application when the load increases. So more copies mean more capacity. But here's the catch. The scaling mechanism was watching the application CPU, not the sidecar concurrency. And because the sidecar was already blocking requests, so barely anything was reaching the application. So the application CPU looked perfectly healthy. So the autoscaler checked its dashboard, saw its screen, and it did nothing. And here's the cruel part. The worse the sidecar got, the fewer requests reached the application, which made the CPU look even healthier. So the outage was getting worse and the graph was getting greener. That's an inverted control loop. The closer you get to the failure, the more confident your dashboard becomes. But the problem didn't stay inside the sidecar. Before we go further, there is another character we need to meet, the load balancer. Think of it as a receptionist as a huge office building. Thousands of people are arriving, but instead of sending everyone into the same room, the receptionist spread them across different rooms and servers. That's basically what a load balancer does. But there is one thing it has to keep track of, every connection that is currently open. And that's where the next problem appeared. The slowdown started moving upstream into the load balancers, where GitHub hit a completely different limit. Not CPU, not memory, connections. Think of a car park. Every open connection takes up one parking space. Once all the spaces are occupied, no new cars can enter. And that's exactly what happened. Several of GitHub load balancer ran out of connection capacity. And here is why those connection tables filled up so quickly. So normally a request comes in, does it work, and then leaves quickly. But when everything slows down, every connection stays open much longer. So the important part of this is, if the request is still waiting, the connection is still occupying a space. So it's like a car park where cars are normally staying in for 20 minutes and suddenly they start staying for hours. So you don't need more cars to fill the parking lot. You just need the existing cars to stop leaving. And sitting behind those load balancers was another critical service, the authentication. So authentication is the probably the worst thing to slow down because almost everything depends on it. issues need authentication, pull request need authentication, actions, playbook, git operation, the API, the copilot, everything needs authentication. So from outside, it looked like several completely different GitHub products were failing at the same time. But underneath, they were all hitting the same bottleneck. Now there's another interesting question. Why did the traffic get so high in first place? And this is where AI enters in the story. We all are using coding assistant now, generating code, asking for completions, and making requests at a scale that simply didn't even exist few years ago. And every one of those requests eventually needs an authentication. So normally, a copilot's token traffic is around 7,000 to 9,000 requests per second. During that incident, that jumped to roughly 70,000 to a lakh. So that's around 10 times the traffic. And GitHub didn't suddenly get 10 times more user. The problem was retries. And this is where the human behavior makes everything worse. Imagine you are sitting and waiting for Copilot to respond. Nothing happens. You wait a little longer, still nothing. So what will you do? You will try again, still nothing. You will try again. Now imagine millions of developers doing the same thing at the same time. But it was not just the humans pressing retry. The software was doing it too. When a request timed out or failed, clients or internal services could automatically retry it. And retries are not inherently bad. They are because transient failure happens all the time. The problem is what happens when you keep retrying service that's already overloaded. Now you have people retrying requests while software is also retrying the request in the background. And this is where a slow system can turn into a completely dead system. A request becomes slow, so the client retries, but the original request is still in progress. Now the server is doing two jobs for one user. That makes it even slower because that causes more timeouts, which causes more retries. And now you have created a loop where every retry makes the original problem worse. Two things made GitHub's retry storm particularly bad. First, some internal services were also retrying against the same load balancer that were already struggling. And second, there was a latent bug in VS Code retry logic that would multiply traffic for a particular slow endpoint. So now the system was not just dealing with original traffic, it was dealing with the traffic generated by system trying to recover itself. And this is the scary part. You can't simply ship a hotfix to VS Code in middle of an outage. It's already installed on millions of machines, and those machines are already hammering your servers. So GitHub's most immediate lever was on the server side. And eventually, they disabled the problematic authentication token retries. And that's when things finally started improving. They ended up turning off a resilience mechanism because under these conditions, that resilience mechanism was making the outage worse. But even after the system started recovering, the problem was not immediately over because bringing a saturated system back in is often harder than keeping it running. And all those developers who were retrying throughout the outage are still there. The moment capacity comes back, they all can hit the system again. So you get another wave of traffic. The system recovers, traffic comes back, it gets saturated again, and you repeat the cycle. So what actually took GitHub down? It was not one thing. The sidecar hit a concurrency limit, but the autoscaler didn't see it because it was watching the application CPU. That allowed requests to pile up and contributed to the connection exhaustion in the load balancers. Authentication started struggling, which affected multiple GitHub services, and then retries kicked in. Humans were retrying, clients were retrying, internal services were retrying, and those retries multiplied the traffic going into already saturated system. Then VS Code retry bug amplified the traffic even further. So you had a small capacity limit, the wrong scaling signal, exhausted connections, and then a retry storm all feeding into each other. That's what turned the local bottleneck into a platform-wide outage. And this is the part I really want you to remember. Look at every component in this chain. The sidecar imposed this current concurrency limit, correct? The autoscaler followed the metric it was configured to follow. Correct? The load balancer enforced its connection limit. Correct? The clients retried their failed request. That is also correct, at least in principle. And yet, the entire system still went down. That's the scary part of this distributed system. You don't always need one component to completely fail. Sometimes every component can behave exactly as designed and the system can still fail as a whole. So what can we actually take away from this? First, look at what your autoscaler is watching. If there is a proxy in front of your application CPU might not tell you anything about the proxy health. Second, be careful with retries. Use exponential backoff, add jitter, have a circuit breaker so your system knows when to stop trying. In simple terms, don't let every client retry immediately at the same time. Wait longer in between the attempts and add a little randomness so everyone doesn't come together. And third, don't just watch the CPU and memory. Look at connection counts, file descriptors, ephemeral pods, queues, and every other resource that has a hard ceiling. Because sometimes the metric that kills your system is not the one that's turning red. It is the one that is staying beautifully green. Thank you for watching.